Friends, today we are now going to discuss analytic function. Analytic function or analyticity in case of complex variable. What do you mean by analytic function or analyticity in case of complex variable? Let's discuss. In the previous video, we have discussed about differentiability and we have discussed about continuity and limits. So in this today's video we are going to discuss one of the most important thing, that is the analytic function. What do you mean by analytic function? So let's discuss about this. If the derivative such that f dash z, if you have a region, suppose this is a region, okay, this is a region where all points of z's of a region are. This is a region, all points z of a region are. Now if the derivative f dash z of any function f of z, if the derivative of the function f of z, f dash z exists at all point of z in the region R, then fz is said to be analytic in this region R and is referred to as analytic function. That means, suppose you have a region. Let me describe you very clearly. Suppose you have this is a region. Here all points in this region, are. Now here suppose here's so many points. There are so many points here. Okay, there are so many points. Let us take a point. Suppose here it is a point A, here it is a point B. There are so many points in this region R. Now f of z, when we will say that f of z will be analytic? When the derivative of the f of z, will exist, when the derivative of the f of z exists, these all points in this region are, when the derivative of the f of z will exist all point in the region R, then f of z will be known as analytic function in this region R. Actually, analyticity is the properties of region in a certain region, not of any point. Analyticity is the property of region, not any points. That means if fz, if the derivative of a function exists all points in a region R, then that is analytic function, and it is known as regular function or holomorphic function. Now suppose you some of you say that if it is a properties of region, so we are discussing points also. How can we say about the points, analyticity about the point? F of z, it will be analytic at a point z0. Suppose in this region there is a point z0. It will be analytic in a point z0. In this point, in which condition it will be analytic? If the neighborhood of this point, neighborhood means if there exists a neighborhood of this point, neighborhood of a point means z minus z0 less than delta. In this neighborhood, all points of f dash z, if these neighborhoods of this point f dash z exist, that means differentiability of the function f of z exists, then f of z will be analytic at this point z0. And I am again saying that it is a property of what? It is a property of region. It is a property of any region. So that is actually analyticity or analytic functions. That means if differentiability, if we get differentiability of any function, if differentiability exists, then the function will be analytic. If differentiability exists, then the function, differentiability implies what? Differentiability implies continuity. Continuity implies what? Then that means it will be analytic. But the reverse is not true. Continuity means differentiability, the reverse may not be true. Okay, so now let's discuss Cauchy-Riemann equations. The main thing, how to prove necessary condition for proving analytic function. What is a necessary condition for proving analytic function? Suppose, and that will be discussed by CR equation or Cauchy-Riemann equation. Necessary condition means what? What do you want to say? Suppose if you have a function f of z, okay? You have a function f of z such that real part of xy plus iota, imaginary function iota into imaginary part of v of xy. Now this is analytic in a region R. That means a necessary then what is the condition? What is a necessary condition? That this function f of z equals u plus iota v will be analytic in a region R. Then u and the analytic in a region R. Then which is a condition for this? Necessary condition for Cauchy-Riemann equation. So the necessary condition for Cauchy-Riemann equation will be necessary condition for CR equation. So what is the necessary condition for CR equation? So necessary condition will be that in a region f of z equals such that real part u plus iota v, real plus imaginary part, if it is such that if it consists of u plus iota v, then it will be analytic in such way. Let me write clearly. F of z equals u of xy plus iota v of xy. Then the main property that it would be analytic, that is Cauchy-Riemann equations. What are that equation? Let me write in a clear page. Cauchy-Riemann equation. What are the condition for Cauchy-Riemann equation? So condition for Cauchy-Riemann equation is that if u plus iota v is the real part, v is the imaginary part, then we can write del u function of xy, v is also function of xy, del u by del x equals del v by del y, first condition, and second condition is such that del v by del x equals minus of del u by del y. So the Cauchy-Riemann equations, the necessary condition of Cauchy-Riemann equations are that del u by del x equals del v by del y, and secondly del v by del x minus del u by del y. Okay, so these are the Cauchy-Riemann equation in a region R. Now it is a necessary condition that fz will be analytic. That means if the partial derivatives are continuous in region R, then Cauchy-Riemann equations are sufficient conditions that fz will be analytic in region R. So let's discuss more clearly. Now u and iota v. Now there is one more important thing here I have to discuss must, that is harmonic function. After that I will discuss numerical also. I will discuss some examples also about this analytic function. So what do you mean by harmonic functions? First discuss that harmonic functions. Harmonic function means we have studied that del u by del x plus del u by del x equals del v by del y, and del v by del x equals minus del u by del y. That is the condition for analytic function. So if the second derivative of second partial derivative of u, second partial derivative of u, second partial derivative of u and v with respect to x, okay, and y second partial derivatives of u and v with respect to x and y exists and continuous in a region R, then how can we relate that? That means, suppose in a region R there is fz. Fz is containing what? Fz containing u plus iota v. Now we say that if f dash in all the points in this region, if f dash z means differentiability of that function f of z exists, that means in the all points in the region differentiation of fz exists, that means f prime z exists, then it will be what? It will be analytic function in these all points in this region. Okay, so fz equals u plus iota v. Yeah, now u plus iota v means, now if we do second derivative, u plus iota v means what? That means first derivatives of u and v with respect to x and y. Now if you do second derivative of u and v with respect to x and y, del to u by del x square and del to u by del y square. Similarly, del to v by del x square and del to v by del y square. That means second derivatives of u and v with respect to x, second derivatives of u and v with respect to y. If these both exist and these are continuous in a region R, if these are continuous in a region R, then we can say, then there is a relation. What is that relation? Del to u, let me write clearly. Why pen is not working? Yeah, here it is working. Del to u by del x square plus del to u by del y square equals 0. Similarly, we can write, let me write clearly, del to u by del x square plus del to u by del y square equals 0. Similarly, we can write del to v by del x square. Let me write clearly. Del to v by del x square plus del to v by del y square equals 0 if these are the condition for harmonic function. That means second derivatives of u and v with respect to x and y, these are continuous in a region R. Then we find that del to u by del x square plus del to u by del y square equals 0 and del to u by del x square plus del to u by del y square equals 0. This is the condition for harmonic function. It follows that. What it follows? Now you have to think that what it implies. What it actually implies. It implies that real and imaginary parts are analytic functions that satisfy Laplace equation. That means, suppose if someone has given you a function f of z u plus iota v, and he or she is asking you whether u is analytic or not. How you can prove? So you can prove by, that means del to u by del x square plus, you can prove by this relation if u satisfies the condition del to u by del x square, sorry, pen is not working properly, del to u by del x square plus del to u by del y square equals 0. If the second derivatives of u with respect to x and y, and if we get such relation, then we will tell that u is analytic in this region. That means real part of that function is analytic. We will clearly understand about this concept in our next video by doing problems on this. That means fz equals u plus iota v. Suppose someone is saying, how can we say that v is analytic? Then we will show him that del to v by del x square plus del to v by del y square, if it is equal 0, then v is analytic. We will do problems and some numericals on this topic in the next video. then you will be clear about this concept. So that's it for today. The next video is coming with problems and numericals of this analytic function. It's very much important of this complex series. So thanks for staying tuned, and thanks for staying connected. Bye.